I am David Cantor, one of the founders of MLCommons and the head of MLPerf. And so it is my extreme pleasure to be able to kick this off. And I also want to thank everyone for taking the time to join us this morning, everyone from the press and analyst community, everyone from the MLCommons community. We've got a ton of submitters who've worked incredibly hard. We've got the chairs of the working group who have put in heroic effort, folks within the MLCommons team who have similarly put in heroic efforts to bring this together, in part because this is one of our largest benchmark rounds ever. So if we can go to the next slide. Um, as per usual, we have a Google Drive that will contain much of the information. Um, there was a error in some of the results ingest, and so we are actually updating the results as well as the supplementals, and those will be distributed later today. My apologies, but there are bugs, and I think this actually highlights part of the value of the peer review process that we engage in. Is that the saying with enough eyes, all code is shallow, and we get to find all of the bugs. Um, so those will be distributed after the press briefing. All right, next slide. All right. Uh, so this is the agenda for the day. I get to kick off the intro, and then we'll turn it over to Curtis to talk through sort of what the storage working group has been up to, including our new benchmark for storage, the checkpointing workload, which I'm thrilled to have. Next slide, please. So as background for those who don't know us, MLCommons is a industry consortium. We are an open nonprofit that is dedicated to making AI better for everyone. MLPerf is one of our marquee projects. We have tens of thousands of benchmark results across many different benchmark suites. As I like to often say, everything from microwatts to megawatts. MLPerf Storage is one of our newest and emerging benchmark suites. And I'm particularly proud of our accomplishments. We've got over 125 members spanning the globe, 6 out of 7 continents. And as I will always do, if you have friends in Antarctica who would like to become members, please send them my way. 6 out of 7 is, still leaves room for improvement. In addition to focusing on benchmarks for performance, one of the key areas that MLCommons is active in is powering data for AI. We work on standards like the Croissant metadata standard. We've released many data sets, such as the multilingual spoken words corpus. This is part of this is because ultimately data drives AI. And of course, data needs somewhere to live, which brings us to storage and the next slide. So the philosophy of MLPerf started with MLPerf training, but applies to all of our benchmarks. We want reproducible results. This ensures reliability. This ensures that you can apply the scientific method, that once you start measuring things, you can improve them. We want representative workloads that are meaningful with respect to production use cases, so that as we optimize for these benchmarks, we are creating value for the entire community, for all of our downstream users, for all of our partners, for all of our members, for everyone. We want to help it drive innovation. And then we want to have a fair and open process for performance measurement that brings together commercial and research community. And as Debo has pointed out, affordability is actually super critical. And one of the key innovations in MLPerf Storage is that it is a benchmark for storage systems for AI, but it does not have the requirement of building out massive storage systems so that you can study and look at what is the storage you might need to train a trillion parameter model to do the checkpointing for that without having to actually have a system capable of training a trillion parameter model, which is in the hands of relatively few. Next slide. Uh, Again, machine learning is a full system problem that encompasses everything from the lowest levels of silicon, whether it is transistors for compute, whether it is NAND flash, whether it is hard disks, including network, including software, including algorithms, architecture, the scale. Everything is used to optimize for AI. It is a full system benchmark. And this is beautiful in that it gives us a lot of levers to pull on to improve performance. But it also makes measurement extremely challenging, right? Because we have to account for all of these variables. Next slide, please. So before we turn this over, I want to just share a brief anecdote, and I want to invite Debo to say a few words. So MLPerf Storage started out a long time ago, and in a lot of ways, it was Debo's idea. And he made the comment of, "Hey, we've done a great job doing MLPerf training, MLPerf inference. We've set an industry standard, but storage is out there. We need to do something there." And that was the inception of something that was great and would grow. And we have a huge number of submitters, more submitters than any other benchmark to MLPerf, which is incredible considering that this is our third round. So, we started small and have grown incredibly mighty. Debo?
Yeah, thanks, David. And actually, to add some more color, it was not just my idea. It was David and I. We were chatting over an MLPerf, meetup, our quarterly meetup meeting, and we looked at a recent paper, then recent paper from Facebook/Meta, and we realized that we need to do something about storage. And we also realized that storage, as training systems become larger, and there were none of those problems that we have today on the inferencing side, like KV cache offload. But just for the training, we felt that storage will get redefined. But in order to redefine storage, you need a benchmark. You need large data sets, and you need the whole machinery. So I'm delighted to see that from that one small hallway conversation, we've come to this point, and it's been a delightful experience working, seeing the community grow. And kudos to the co-chairs, all the four co-chairs who work like us, who work very intensely to even define this benchmark. And as we grow, and I mean, I'm sure there'll be a roadmap with more workloads. But I can see that all this while we had focused on training, but as multi-agentic systems will proliferate, you'll see more needs to do inference, benchmark, scaling compute on during inference. And because of that, there'll be a lot of KV cache offloads and all that. So I think this benchmark will continue to grow.
Yeah.
And can't wait to see what comes next from these four talented co-chairs and the community.
Absolutely. And so thank you for inspiring this. It's, this is one of the beauties of having a community and bringing things together is, sometimes a small hallway conversation grows into, tens of companies coming together to help drive the industry forward. I want to say a special thank you to, as Debo said, to our working group chairs, Curtis, Juana, Janu, and Huiho. They've put in tremendous effort. The MLCommons staff has been working tirelessly on this, especially given that yesterday, for those of you who don't know, MLPerf Client was released. So you can now download a PC or Mac client to measure ML performance. As an organization, this is literally the first time we've done 2 launches back to back. So, we're setting all sorts of performance records ourselves. Um, and a special thanks to all of our submitters. I think next slide. And Curtis, am I talking through this or are you?
I think you've got 3 more slides.
Okay. Yeah. So ultimately, part of the reason why storage is so critical is that data, as I mentioned earlier, one of the reasons why MLCommons builds data sets and works so actively in data is that data ultimately is what drives AI capabilities. This is a slide taken from a paper from Baidu Research. And for many of you, you may have heard of large language model scaling laws. That's a very specific form that is a more specific instance of what this chart shows, which is on the x-axis, we have the size of the training data set in log scale. And on the y-axis, we have the generalized error, right? So on the y-axis, lower means more accuracy. And really what this shows is that the challenge and the problem with AI in the 80s and the 90s, and even in the early 2000s, was we didn't have enough data, right? And when you don't have enough data, then you don't get good accuracy. And, something like asking an expert system or asking an expert is simply better. You're in this best guess regime. But when you hit this point, this power law region, all of a sudden more data starts translating nonlinearly into better performance. And somewhere along that curve is better accuracy that allows Waymos to very safely roam the streets of San Francisco, that allow image classifiers to beat humans at recognizing images. That was the catalytic moment, AlexNet in the ImageNet competition, where many people realized that actually AI was here to stay. That is what allows large language models to produce so many valuable insights, right? And the key here is it's data that drives this, and that data needs storage. Next slide, please. And this is, as Debo alluded to, there was a paper from Meta that really had this great insight that, yes, the capacity of data that we need is growing. And, this is, again, normalized, but this is in production from a company that is on the frontier of AI in many different ways. But not only is the capacity growing by a factor of, 2x over 2 years, which is pretty rapid, but the need for data ingestion bandwidth is growing even faster. And so there's some very non-obvious ways in which storage is a really key element. Early on, years ago, we heard reports of folks who had deployed large compute clusters that were underutilized very significantly because the storage systems were under-provisioned, right? And what that pointed us to is that is an opportunity for a benchmark to form, to shed light on that challenge, and to help the whole community start focusing in on these problems. And that will allow us to make ML more capable and in the hands of more people and working its magic in new and exciting ways. Next slide. So it is now my extreme pleasure to turn this over to Curtis Anderson, who is the MLPerf Storage, one of our working group chairs, who has been shepherding our brave companions, our of submitters and volunteers forward. Curtis, please take it away.
Sure, thank you. Let's see. So MLPerf Storage overview. First off, you have to define why you're interested in measuring storage, right? That storage can be a bottleneck. Storage can be an enabler. The performance of the storage, feeding all that data to the compute cluster is a large challenge. The size of at the upper end is just extreme for large language models, training them, but the size of your typical models is also growing. And so there's just everyone is going to experience this growth in data. So it's the purpose. to understand at a theoretical level and a practical level what about storage could be improved, where the bottlenecks are. We also want to help the AI practitioners, the people on the ground that actually have to build and run AI environments to make informed decisions about the storage. If I have this size of AI problem, will this particular make and model of storage solution be sufficient for this, or do I need something better or different, right? And then we'll talk about the specifics of the two different types of workloads we talk about, or that they're measuring in version 2.0 in a minute. We also want to help the storage suppliers optimize their products for the AI ML workloads. If you measure it, you can improve it, the old saying. And so some of what you'll see in the results is, because there is comparable results from us over time. 3D UNet, for example, is a particular workload, and we've had 3 different rounds of results for 3D UNet. So you can look at and we've had several submitters who've participated in all 3. You can look at the performance of their product over time and say, oh, look, they've been improving the function and performance of their product under that workload. And lastly, the AI frameworks, PyTorch, TensorFlow, those libraries that make all the rest of it easier to do, they are built by data scientist people who are focused on the AI and ML. And we want to bring a storage understanding to them to say, oh, if you can have all of that, the goodness you want for your data scientist customer, the people who are using libraries. But if you change these things, you can get more storage performance for the data scientist people. That's another one of our goals. Okay, so quick review of the structure of training so that we can say, okay, this is how we simulate training. So in general, you've got a data set living on a disk. You have system main memory, DRAM, and you have the accelerators, GPUs, ASICs, whatever. The accelerator is going to be computing on a batch of data, and the framework is going to ask the storage, hey, I need the next batch of data sitting in memory. So as soon as the current batch finishes, I can load that in, and then the computation continues. That's sort of the normal data flow. For some workloads, there is also online pre-processing where I won't go into great depth because I'm a storage guy, and the AI people will probably look askance at me if I get it wrong. But you can multiply the effective amount of data, like you take an image of a cat and you rotate it a little bit, or you change the color palette. It looks different. So this is what pre-processing is. You can multiply the amount of data, the effective amount, by doing these small tweaks to things as they go through. Now, having said that as a sort of mental model, what the benchmark does is it uses the same code that lives in the frameworks, PyTorch and TensorFlow specifically, to load the data off of storage into system memory. But we don't actually bother putting it into the GPU or the accelerators because we don't require that. It's one of the affordability things in the benchmark, is that we make a simulation of what the AI workload would look like without actually having any of the hardware. That makes it much more practical for a storage supplier who may not have a whole lot of accelerators hanging around doing nothing, to impose large workloads on their storage and do a lot of iterative testing. So that's what we do. We get the data into main memory, and then we will and simulate the computation time by just doing a sleep. The process waits for the 325 milliseconds that 3D UNet takes to do its thing, and then we'll get the next batch of data. Okay. Significant variables in training. We'll talk about checkpointing in a second. So the PyTorch, the framework matters. PyTorch and TensorFlow are very different in how they store the data sets, how they store the data samples. The amount of metadata processing required by PyTorch, for example, is significantly higher than that required by TensorFlow. TensorFlow has a different data layout. They put many samples into a large file, and PyTorch just stores one data sample per file. So you can see where the metadata load comes from. Now, they each have PyTorch and TensorFlow have their advantages for the data scientists. We're not trying to push one or the other. We're supporting both of them. And there's, I don't know, 2 or 3 dozen more of significant importance to the community. These are just the ones that we're supporting today. Storage network. How the storage is connected to the computation host, that's important. Do you have enough bandwidth to get the data through? Do you have enough ability to support the latency requirements? There's a lot, if in PyTorch, you have to open a file, read the content, and close the file, and there's a lot of latency involved typically in that exchange. Hardware and or software that runs the storage, that's obviously important. The type of training, there's single host, and which is typically done for the smaller workloads, the smaller problems today, or for experimentation. You're trying out a new approach. You don't really need 1,000 GPUs in order to do that experimentation. So data scientists on their workstation or desktop, for example. So that is just different than either a large language model or something that's using a couple of accelerators, or maybe a couple of nodes with several accelerators each. The storage workload is very different. Type of data, images versus text samples, obviously different sizes. Caching is the sort of, not quite the bane of our existence as a benchmark, but it's a really important thing. Caching is great for performance, but eliminating caching as part of the benchmark in order to show a repeatable, accurate measure of the storage solution independent of the client that's doing the accessing, we have to prevent caching in order to get that measurement. So it's a significant variable for us, to put it mildly. Okay, so what's new? Well, we have the 3 training workloads, 3D UNet, CosmoFlow, and ResNet 50. They each represent a particular class of application of AI technology to a particular requirement, right? ResNet 50 is really good at recognizing images. So you can imagine a factory, got widgets going past, ResNet 50 can tell you, oh, that one's formed correctly. Oh, that one's not formed correctly, the widgets, where that your beer bottle is full and that one's not, for example. So we have the training workloads. Those are continuing. The new one was checkpointing. So at the upper extreme, it's easier to explain there. Llama 3, Llama 4, those the large language models that have the 8 billion, 70 billion, 405 billion, and 1 trillion parameters in model. Those are enormous. Those take a lot of hardware, thousands of accelerators, and still take a month to do the foundation training. When you have that many accelerators in one spot, the mean time between failure will catch up with you, and at least one of them will have a problem, or maybe a whole node, right? It's not always the accelerator. Will have a problem, and the computation comes to a halt because you need all of them to do the computation. So you take a checkpoint. Every so often, you write the state of the entire computation out to stable storage, and then you continue. And if there's a problem, you just back up by one checkpoint, and you pick that up and continue on. So, as I said, there's 2 kind of things you're protecting against: infrastructure interruptions, such as crashes or networking problems. But there's also a more subtle thing that data scientists care about, which is low convergence rates. They have a particular tweak to their neural network model, and they say, well, let's train it and see how it goes, but it's not converging to a high quality, high accuracy model, predictive model. And so they go in and they want to change something, but they don't want to start from the beginning, so they start from a checkpoint. Checkpointing applies more to more types of jobs than just large language models, but we use LLMs because it's really, really obvious why you need a checkpoint at that scale. Anything that takes more than a couple of hours may benefit from having a checkpoint in it, even the smaller jobs. So something else that's new in 2.0 is normalization factors. So in 1.0, the press and analysts were diving through the data, looking around saying, oh, this is great. Look at all this information. And then they said, okay, but wait a minute. How do I compare these two entities, these two rows in the table? Can I divide by the number of clients? No, because the number of clients for us in the benchmark is deliberately constructed so that the number of clients is not a relevant predictor of performance. So these we call normalization factors. How does someone normalize to a consistent unit? So we're now requiring rack units for the storage solution under test in version 2. So you should be able to say performance per rack unit on a particular workload. We are in the process of building out to including consumed power as part of the benchmark. What we have in this benchmark is provisioned power. Now, provisioned power, you'll see there's a note there. You have to dig for it in the YAML files. Provisioned power is, I'm about to build a data center. I want to put 1,000 accelerators in it. The little nameplate on the power supply says I can draw a maximum of 8,000 watts per power supply. You multiply, that's your provisioned power. Consumed power is what you pay your power company every month. And that can be a lot less, like 10, 20% of the provisioned power. So we asked for provisioned power from our submitters this time around, but we're not publishing it because of I mean, it's there. You can find it if you go looking, right? But we're not publishing it in the easily viewable table because of the risk of people making the wrong conclusion. Oh, yeah, I can give you this many gigabytes per second from the storage system per watt of provisioned power. It's important to know provisioned power, but it's not the same as consumed power. So that's the reason that it's not front and center for us. But in version 3, we plan on having consumed power as an optional data point for the people who are submitting. And so then you really will be able to say, okay, now this makes sense. Performance per watt consumed is a really good measure. Okay. So what is checkpointing? What does the storage workload look like? You're gonna the training job is going to run checkpointing periodically to save progress. You can see that scale and size back up. So a training server, you can see here in the diagram, it's got this is an accelerator. We use the term accelerator rather than GPU because there are more pieces of silicon out there than just the NVIDIA product, and we try to be nonpartisan. So the accelerator has the model. There's also a piece called an optimizer. Now, me as a storage guy, I was introduced to optimizer about 8 months ago. And said, oh, that's interesting. It's different, something I hadn't known about. So the model is in a 1 trillion parameter large language model. The model is the 1 trillion. There's another thing called an optimizer that helps during the training process. I've heard it described as remembering the shape of the gradient descent, the graph inside the training model in order to help you decide where is the fastest way to train. Is it this direction or is it that direction? So in practice, the optimizer state is on the order of 6 times larger than the model itself. So when you take a checkpoint, you need to record on stable storage the model and the optimizer state. So the 1 trillion parameter large language model takes about 18 terabytes to record the model and the optimizer. The 1 trillion parameter, if it's FP16, that would be 2 terabytes just for the model. But the other 12 or 14 terabytes out of the 18 comes from the optimizer state. Just an interesting insight for me, at least, on the mechanics of what goes into training. And obviously, we want the accelerator to be as productive on the computational problems we possibly can. So the time required to move the model and optimizer state out of the accelerator to main memory, and then the computation can continue. Then we're going to move what's in main memory out to stable storage while the accelerators continue to do its job. That turns into what storage people would call a denial of service attack. you've got literally millions of IOs hitting you all at the same time, all for enormous amounts of data. In practice, for example, you could have an 11 gigabyte buffer sitting in main memory, which is the combined model and optimizer state. And there's a single write system call that says, put the whole 11 gigabytes on storage right now. The file system will break that up into tractable chunks, and all those chunks will hit the storage system like a hammer all at the same time. So it's a very, from our point of view, it's a very dramatic workload. So checkpointing is not just saving the model. If you need to restore from it to back up, you had a failure of some kind, a networking cable went out, whatever. You want to be able to restore the state of the computation from that checkpoint. Note that in this environment, when you're doing this, all of your accelerators are idle. They're waiting. And you need to get that checkpoint back into main system memory and into the GPU, the accelerators, as quickly as you can. So the read performance, the read bandwidth getting into memory and the latency of getting that all done is extremely important. So the benchmark, in order to represent a variety of sizes, we model an 8 billion parameter large language model. That might be something embedded in a home automation device or something small. 70 billion or 405 billion might be a chat bot on a website for a company. The 1 trillion is the large reasoning models, the really big guys. There's a bunch of parameters here: data parallelism, tensor parallelism, pipeline parallelism. I won't go into all that. The checkpoint sizes you'll see here, they're large. The breakdown between the model and the optimizer state is just below that. We allow the submitter to actually run a simulated workload of the 8 billion model is 8 processes on one node. The 70 billion model is 64 processes spread across 16 nodes, 8 processes per. You can see the 1 trillion model is 1,024 instances of the benchmark, all operating across, I think it's 64 nodes, I think is the number. I'd have to look that up. But in order, the 64 pieces of hardware and all the networking gear, that's a large expense. So we give the option to the storage vendors that if your architecture, your storage system architecture is obviously linearly scale out, for example, as I've got an NVMe drive inside the compute node, then that's part of the reason that NVIDIA includes NVMe drives inside the DGX products is for this exact reason. Again, I'm not shilling for them, but it is why those are there. So if you have that linearly scale out architecture, then you can do a subset where you'll see these in the results. It's 8 processes on one node, and you just multiply the result times the number of nodes you have because it's scale out, linearly scale out. And you can see the size of data that is written by the 1 trillion, for example. That's 144 gigabytes that need to be flushed to the local storage as quickly as possible. We had 16 submitters and 74 results on the new workload. 26 submitting organizations overall. Challenges. We've talked about the model FP16, the optimizer is FP32, and so that's part of the reason it's larger. The ratio of sizes. Talk a little bit about the synchronous saving. It can be overlapped with computation, whereas restarting from a checkpoint cannot be overlapped with the computation. So in one sense, the reading of a checkpoint is more interesting. It's the bandwidth is more critical to the end customer, even though restarting from checkpoints is much less frequent than saving checkpoints. We have a blog that talks about the math behind optimizing how frequently you should take a checkpoint. And so that's you should go look at that. It's a geek out on the numbers. Um, and we talked a little bit about the bursty access, that it's a denial of service attack against the storage system. Just bury the system underneath an IO workload. It might seem straightforward. Oh, it's all purely sequential in large files. Yeah, except that that it all drops on your doorstep at one time. Oh, and so here's another interesting thing at the bottom there, that the checkpointing workload for the 1 trillion parameter model is on the order of 10 petabytes per day being written. And so that's a large amount of data being written to your storage. Um, we have actually quite a large number of individual SSD manufacturers that are in the working group running the benchmark, and they look at that and say, "Man, that's gonna put a strain on the wear life of the NAND. We have to plan for that. You have to make sure that the customers are going to be happy with that level of writes per day." So overall, here's the summary. We have the three training workloads on the top of the table there, and there's the new checkpointing workload. Oh, geez, running a long time. I think that's about it. Results overview. You can see the cloud. We have 26 submitting organization with over 500 performance results. Um, the list of people and the highlighted ones are new to MLPerf today. MLPerf Storage.
I think we have a slight bug in the counting. It's, I think, just under half of that in terms of performance results.
Oh, yes, you're right.
There's a
Thank you.
mismatch between the rows in Tableau and the number of performance results.
That's true. You're right. We wrote these slides a couple of days ago, and then as we were working through getting the Tableau stuff up, the number was different than we had thought it would be. So key insights. This is kind of the same list as before, but not the same actually. Explosion is driving a wave of innovation in the storage. AI is driving storage to do different things. Storage is a hidebound business. I can say that because I'm a storage guy. And storage, because there is such an extreme need of focus and need for reliable storage system, you can't lose data. People are hesitant to take architectural risk with new architectures unless they have to. And now AI is making us all in the storage business take those risks because we have to. And so it's an exciting time to be in storage finally and again, because things are changing. So just as at the highest level, training, distributed training is a mix of bandwidth and metadata IOPS. Okay, storage systems know how to do that. Checkpoint is dominated by raw bandwidth. Checkpointing has been in the HPC market for a long time, but possibly not at the same scale as the AI market is driving it. And inference is dominated by raw data IOPS, not metadata, but data IOPS. And the database Oracle type, relational database workloads are also dominated by that. And so that's an interesting difference that, anyway. You as the press and analysts, we ask that you appreciate the amount of work that the submitters put into producing these numbers. It is a fair amount of effort to optimize the storage for the workload being imposed on it, to understand the benchmark and the workloads well enough to say, oh, this is a fair change. I can make this change, or oh, this change that I would like to make to my product doesn't actually help the end user, and so there's a lot of work went into it. Be wary of how to normalize results. It can be tricky to get something that makes sense, like bandwidth per accelerator. You might think, oh, I'll just divide by the number of accelerators. But the way the benchmark is constructed, what you end up with is a constant number. Everybody has the same bandwidth per accelerator. because that's the way the benchmark is constructed. So just be a little wary of that. We in the working group, we're happy to take questions now or over time to help you understand how this all works together. And now finally, 15 minutes left. Questions?